In this lesson, we are going to talk about shadows. Now that we have light, we want shadows, obviously. We already have some kind of shadows because if you look at this sphere, you can see that the light seems to be coming from my upper right, and at the other side of the sphere, I get something darker. This is called core shadow, and core shadow is obviously already working. What we want right now are drop shadows. We want to see the silhouette of the sphere on the plane, the shadow silhouette on the plane. And this is what we are going to do right now. Shadows have always been a challenge for real-time 3D rendering. Every time, like video games, stuff like that, it's always a challenge because you need shadows at a good frame rate. When you are using 3D software like Blender, C4D, stuff like that, you have an option which is ray tracing. In Blender, you also have real time, which is really interesting, but you usually use ray tracing to have good results. And ray tracing is very, very long. Like it can take hours to do one render. We cannot afford hours to do one render. We need to do at least 60 renders per second on medium computer, so it's not an option. We need real-time options with good performances, and we're going to discover those solutions. 3GS has built-in solution. We are going to use this one. It's not perfect, but it's really convenient. With just few lines of code, we can have great shadows. But first, how it works. When you do one render, 3GS will do a render for each light supporting shadows. In our scene currently, we have a directional light. When we will ask 3GS to do one render, 3GS will also do one render for this light, another render. Right before our render, 3GS will do a render for this light. Those renders, those light renders, will simulate what the light sees. So it's like if I put my camera right here and do a render of this. Those lights render, during those lights render, the materials will be replaced by the mesh depth material. And we already saw this one. This will enable depth information. All right. It's a little more complex, but the idea is to get the depth of things. So when 3GS does the render, 3GS will replace all those materials by a depth material. The lights renders are then stored in textures, and those textures are called shadow maps. The shadow maps are just textures of what the lights can see. It's not exact to say about what the light sees, but let's think of it like that. Those shadow maps are then used on every materials supposed to receive shadow and projected on the geometry. We need drawings. We always need drawings. So this is our scene. Like that. In our scene, we have objects. Let's say a cube right here. I'm going to have, I don't know, a sphere right here. And maybe a cone right here. All right, in our scene we have lights. So I'm going to have a point light, which is going to be like slightly above the ground, somewhere here. So it's going to be point, like this. I'm going to have, let's say, directional light. So it's going to be there. So directional light will look something like this. I'm going to put directional, like this, and then we can have let's say spotlight over here watching like this. I'm going to write spot. Okay, we will use those during the lesson. First, we are going to talk about, let's say, the directional lights. What I just said is that when we ask to do, no, we are going to use the spotlight. When we ask 3GS to do a render, before doing this render, 3GS will position the camera like here. So this is the camera before our render. It will look something like this. Not bad. And we'll do a render of this, what the spotlight can see. it will store this render. So it's going to be like, let's say in an image like this. And in this image, we will be able to see a cube. It will be with a depth, but still we will be able to see a cube, maybe a sphere here, and a cone behind, something like that. All right, this will be saved on a texture, and this is, I will just put it there. This is what, it's the same thing. I just draw. It will look something like that. We will have, I don't know, the sphere here and the cone here. And this will be our shadow map. You don't have to do this, and you don't even sew the shadow maps. If I have like 100 spotlights, I will have 100 shadow maps. You cannot have 100 spotlights in your scene. That's a bad idea. Okay, anyway, that's the idea. When we will do the render of the scene, once we have the shadow maps, so once Three.js did the shadow maps, Three.js will take those shadow maps and use them to color our objects, our geometry, our meshes. So Three.js will take this shadow map and we add shadow because Three.js knows that there is something here for this light, something here, something here, something here. When drawing our plane, Three.js will understand that because there is something here in this shadow map, well, this is supposed to be in the shadow. And because, so it's going to be something like that, because of the spotlight. Then for the sphere, you can see that there is a part here which is hidden by the cube. Then we will be able to see like the cube shadow here. And same thing for behind the sphere, because this is in the shadow, there will be a shadow right here, something like that. Yeah, this is my limit in terms of drawing. Same thing for the cone, we get something like that. So using the shadow map, Three.js will be able to color, to make those parts darker in the plane, in the sphere, in the cube. The cube doesn't have shadow on it, but anyway, it could have shadows on it. And it will do that for every light. Okay, that's the idea. We are going to get back to this drawing right after. And yeah, you don't need, it's just so you know how it works and why you have to this result and why you have to keep an eye on the performances. You don't even need to understand those. Anyway, I still have something else to show you, which is exactly what I did by drawing, but with a Three.js example. In here, we have a directional light going from the top to the bottom of the scene. So this is this huge rectangle. We are going to talk about the lines you see right here. And we have, it's a spotlight too. So it's almost the same thing here. And those renders here are the shadow maps. It's not exactly true, but it's the idea. So for our spotlight, which is this cone right here, this spotlight can see this result. So it can only see the torus knot. But our directional light, which is like this, and we get exactly that, we have our torus knot at the center and our cube on the bottom right. And this is what we get. So those are the depth renders. Those are the shadow maps. Cool. Great example. Thank you to the guy that did it. Okay, let's move forward. Our setup, yeah, as you can see, we have a sphere, a plane as the floor. We want to have the shadows dropping on the plane. We have a directional light, and we also have an ambient light because, as you can see, the back is not that dark. And if I remove, just to show you the ambient light, where is it? Yeah, right here. If I remove the ambient light, as you can see, it's too dark behind, right? It's to simulate light bounce, but this is not the topic of this lesson. So yeah, how to activate shadows. It's not that hard, but optimizing shadows is harder. To activate shadow, first you have to check your renderer. In our renderer, we are going to do renderer shadow map enabled equal true. This would simply say to our renderer to handle shadow maps, because the shadow maps, those shadow maps, we have to be rendered. Well, it's going to be the renderer work. Okay, the next part is about the objects, and this is a question we have to ask for each object of your scene. Does my sphere can receive shadow, so drop shadows, and does my sphere can cast shadow? Same thing for the plane. Does my plane can receive shadow, and can he create shadow, cast shadow on something else? So in our case, it's pretty simple because we have a very simple scene. We are going to go to the sphere part and say, so as you can see, I create a sphere, I create a plane, I position the plane right below the sphere, and I add them both at the end. So my sphere cannot receive shadows because there is nothing above it. So I'm going to use just cast shadow, and that's all, because by default, they are both false. My sphere can't cast shadow because I want to see the shadow on the plane, and my plane can receive shadow. So I say receive shadow equal true. Still nothing, but we have to do that. We are almost there. What we need to do now is activate the shadows on the lights, all right? But only 3 types of light support shadows. We have the point light, the directional light, and the spotlight, which is obviously what I use in my drawings. So yeah, the ambient light won't cast any shadow, which is logical because the light comes from everywhere. The directional light here is going to cast a shadow. So let's go. We can go to our directional light right here and activate the shadow. You can do it anywhere, like right after instantiating or in another part of your code where you handle all about shadows. It's up to you. Me, I will do it right after creating the directional light. And you will use the same keyword as the same property as for the object, which is cast shadow. So my light can cast shadow like this. True. And yeah, we have a shadow. That wasn't that hard. We had to change 4 properties and it's working. So as you can see, my plane can receive shadow. My sphere can cast shadow. We get this result, which is great. And it's exactly what's happening right here. We have a shadow because the shadow map is happening. And if I move the sphere, do not worry, the shadow will follow. And we will do some animations later. Anyway, let's optimize this shadow. Because as you can see, it's not that bad, but seeing from there. So we need to optimize this. Yeah, so first thing, we need to optimize the render size because the shadow map, as you can see here, has a width and a height. So we can change those. Just like we have a width and a height for our main render, the shadow maps has width and height. How to access those? Well, we are going to do it on the directional light directly because this is where the shadow maps are stored. The shadow maps and many more. And you can see those by logging, so directional light shadow, and you see that there is a lot of information in here. So it's a directional light shadow instance. All right, there is something about this in the documentation, but we won't dive into this because we don't need to do so. And we have access to a camera, and we have access to many other things. Like the map size. Here it is. Yeah. So this is the resolution of the render. So it's like 512 for the width and the height, because as you can see, it's X 512, Y 512. And we can improve this. But be careful, if you do like a huge render, it will take the frame rate. So you will have performances issues. So let's go. We can access the map by doing directional light shadow map size, which is exactly that. And the map size is vector 2, and we can change a vector 2 by doing x equals something. But also, and this is new, you can do width equal something. And you can do it for both width and height. and you will get a better result. See? I'm going to toggle. I'm going to do this one divided by 4. You don't have to do it. It's just so you can see. Wait, I'm going to refresh. See, it's looking really bad. And if I do multiply by 2, which is a lot, we get a pretty nice result. It's not perfect, but it's pretty nice. We are going to use 1024. Okay, cool. Keep in mind that you have to use a power of 2 value, and you know that it's about the MIP mapping. All right, we talk about this. Use a power of 2 value. If you don't know why exactly, just get back to the textures lesson. It's at the end of the lesson. Okay, cool. That's already a little better. Because we are doing render, we also have control on the near and the far. Look at this. This is my camera. So this is the light camera. It's not my camera, it's the light camera. When the camera does a render, like we did in the previous lesson about cameras, we can control the near and the far. So maybe the near is over there and the far is maybe over there, like really far, like way too far. We don't need to go that far. We can just move the near and the far so it just fit our scene. So maybe somewhere like this and somewhere like this. This won't improve too much our result. It's mostly about precision, all right? It can have a good, better result, but that won't make a huge difference. Anyway, you have to do it if you want to avoid glitches in the shadow. Okay, but how do we access this light camera, this shadow map camera? Well, it's the same way. We can do directional light, go into the shadow property and see the camera property. And this is a camera. And this is a camera that we know. It's an orthographic camera, which is strange because if you look at this, it looks like it's more like a perspective camera. But this example was about the spotlight. Right now, we are talking about a directional light. And if you remember from the previous lesson, a directional light will illuminate our scene, but with parallel rays. All right, it's coming from everywhere and it's going straight in parallel direction. So to simulate shadows, we don't need to do like a perspective camera that will do a shadow like this for the spotlight. We need to do a shadow that will shadow map that will render like this in parallel, which is why the camera will look something like this. It's going to be something like that. All right. And if it's larger, well, you get a larger camera. Okay. So we have an orthographic camera. And what we can do right now, because we want to control its near and far value and find the perfect values, what we can do is add a camera helper. And this is really, really handy. We are going to create it and you are going to understand what it is. I'm going to do directional light camera helper. Yeah, I know this is too long, but anyway, I like long variables. Camera helper, and the parameter will be this camera. So for me, it's camera shadow. Directional light shadow camera, and I will just move, zoom out a little, and I think that's all. And what you have to do now is add it to the scene. So I'm going to do scene add directional light camera helper. And here you go. You can see the camera. So the camera started at the right position of the light because my light is right here. And the near value is this part, like here. So it's the first, let's say, square. And the far value is far. So there is a problem right here and we can improve this. The near is not that bad. I mean, we can get it closer to the sphere, but the far is way too far. So let's control this. Now that we can see the near and the far, we can do directional light, shadow, camera, near. We can improve the near just a little. It's not that important because it's already pretty good, but still we can do like 1. And as you can see, it's even closer. Okay, you can do 2, maybe. It's getting like really close. We'll keep one just in case the sphere move. Just keep one. This way the sphere can go like in this part of the plane. You will still be able to see the light. Now the far. And the far in my example is 6. And as you can see, it's way better. So we get a really optimized camera that will do the render for our directional light. Cool. Is it different? Not really, but still you can avoid bugs by doing this. Glitches on the picture. Okay, next thing is about the amplitude. Right now it's doing like a huge render which is bigger than the whole scene. So instead of having this really small render, we are doing like a really big square that looks like this and that will render the whole scene, which is way too much. We need to reduce the amplitude, and you can see that, but because right now it's really large. So yeah, let's reduce it. And because it's an orthographic camera, if you remember from the camera's lesson, we have control over the left, right, top, bottom, and the near and far we already did. So we can control so it's gonna be the left, which is going to be, I can use another color, maybe this one. So this is the center of my orthographic camera. This is the distance on the left, distance on the right, distance on the top, and distance on the bottom of the camera, because it's revert. So yeah, we can control those. So let's just reduce those values. And we are going to use the same one as in the example, and it's going to be, can put it before the near and the far. It's the same, don't worry. Top is going to be 2, right is going to be 2, bottom is going to be -2. Obviously, you just have to test those to make sure that it fits your scene. It's up to you, but in our case, those values are going to be fine. And yeah, so this is much better because it's smaller, and right now you can see a difference. The edges are much better because we are doing a render. Instead of having a render that look like this, so you have your render and you have, let's say I'm going to use purple, it's a sphere. So instead of having this, it's not optimized because we have a very small sphere inside at the middle of our render. Instead of doing this, we reduced the render, and we did so we can have a huge sphere. This way you can have much more details on every edges of the sphere. So it's good to reduce the amplitude to have a better picture of our shadow. And this is the result. We get something much better. Okay, be careful if you have like a huge city, you will have to do like a huge shadow map, and the shadows inside the city, like on the streets, stuff like that, will look bad. All right, we have to find the perfect combination. Yeah, by the way, if values are too small, let's say I'm going to reduce the far. Yeah, the far will be fine. Let's try to find a wrong value. So I use 3, maybe 3.5. Yeah, see, it's getting cropped. 3.8. Yeah, this is the result. As you can see, my render didn't render things too far, and we get this strange result because it's being cropped. So if there is a shadow that looks just cropped, maybe you did a mistake with the camera top, right, bottom, left, near, or far. Okay, once we are happy with the shadow, we can just hide it. The camera helper. So the shadow map, we can hide the camera helper by doing visible equal false on the camera helper, because it inherits from the object 3D, and we can hide objects by doing visible false. Cool, which is great. You can also remove it, but I like to keep them somewhere. I usually just comment them. Okay, cool. We have also control on the blur of our shadow, and we can control it by doing directional light, shadow, radius, and use a different value, let's say 10. And we get a pretty cool result. Test on your screen, but you have a different result. Be careful, this is just a general blur. See, it's not about the proximity of the object. As you can see, the blur seems to be the same here and here, but still it's pretty good. Like seeing from a little further, it's fine, it's looking great. Okay, cool. Next thing is about shadow map algorithm. There is actually a lot more properties, but these are the main properties you should just tweak. The next one is the shadow map algorithm, which will change a lot the result. We have access to different algorithms. The current one is the PC shadow map, which get this result, which is pretty good. We also have access to a basic shadow map, which is more performant but loosey quality, so it doesn't look good. We have access to the PCF shadow soft shadow map, which is almost the same but with the soft part, which will look better, but performances are going to be a little worse. And at the end, we have the VSM shadow map, really strange result. It's less performant, more constraint, and you can have unexpected results, and it's pretty hard to implement. We usually go for the PC soft shadow map if we want to improve this shadow. So yeah, let's use this one. If you want to try the other, just look at the Three.js example. You have great examples and you can implement them and see if you like the style better and the performances. Keep an eye on the performances. So yeah, I'm going to do, no, it's not right here, sorry. It's on the renderer, which is over there. And what we can do is shadow map type equal, and we are going to use this 3 PCF soft shadow map. So it's going to be 3 PCF soft shadow map, and we are going to have a different result, as you can see. So it's strange because we got back the previous thing, but still it looks better than the previous thing. And yeah, that's exactly it. The radius doesn't work with the PCF soft shadow map. Okay, so we can have this this blurry thing we had before with the PCF shadow map. See this blurry thing? If you like this, you can keep the PCF shadow map, but if you want to use the PCF soft shadow map, you will lose the radius, but the edges will look a little better, right? It's up to you, you have to decide on the right solution. Usually when developers want a blurry shadow, they will simply play on the resolution. Like if you lower the resolution, which was 1024, if you do, I don't know, divided by 4, you will get a blurry result, but yeah, it's up to you. You have to find the perfect combination. So we'll get back to my 1024. I can comment the radius because it doesn't work anymore. All right, it's up to you. So yeah, we did it for our directional light. It's looking pretty good. We did optimize it pretty well. Oh, also, by the way, we have access to those properties. So if you want to play with those, play with the intensity of the directional light, the intensity of the ambient light, you can. And see with different materials, you can too. So the metalness and the roughness. So yeah, let's try to do the same for our spotlight, which is the first one we studied in these drawings. Yeah, let's go. The spotlight. First, we are going to create the spotlight. So this is my ambient light, directional light. Well, let's create a spotlight. I will just add a small comment in order to separate things. And I'm going to do spotlight equal new 3 spotlight. We saw this in the previous lesson. It's just a spotlight. I recommend you using my settings because we are going to see a lot of properties, stuff like that. Math pi multiplied by 0.3, so it's the amplitude of the spotlight. We are not going to play with the decay and this and stuff like that. Then we can activate the shadows. So if you remember from right before, we have to do cast shadow true on the directional light. So spotlight cast shadow equal true. Then we can move the spotlight position. We are going to use the set. It's going to be over there. And we can add it to the scene. And don't forget, so it's not mandatory, but still, if we want to your spotlight to look at something else, you better do that. We have to add the spotlight target, which is an object you have to add, an invisible object that you have to add to your scene. And as always, it's not get world position, it's just position. I have to fix this. And yeah, it looks like this. So we are going to talk about this result, but we can already add the camera helper because we are going to tweak this spotlight shadow. Let's add the camera helper. So it's going to be spotlight camera helper equal new, and it's the same class. All right, you can use the same camera helper regardless of the type of camera. New 3 camera helper, and we pass the spotlight, but not just the spotlight shadow for the shadow map thing, camera. And then we can add this helper to our scene like this. Yeah, so this is our spotlight. In fact, it's the spotlight camera helper that we see. But anyway, the spotlight is right here. It's illuminating our scene like that. And this is our result. And as you can see, it doesn't look really good. First, there is too much brightness. So we are going to reduce the ambient light and the directional light. So move up a little and lower the ambient light intensity and the directional light intensity. Because right now it's way too bright and we get this result. Yeah, as you can see, mixing shadows is not physically accurate. All right, you get this strange result, which is not that bad, but still mixing shadows doesn't look really good. So yeah, you better have not too many light creating shadows at the same place. It won't look really good. But still, we are going to improve the quality. So this is our camera. This is the near, which is really close to the camera, and the far, we cannot even see the far. So we are going to fix this, and also the amplitude and stuff like that. So yeah, first we can change the shadow map size, which is the size of the shadow map. We can just crank it up a little. So it's going to be on the spotlight shadow map size. So the spotlight is over there. Yeah, spotlight shadow map size, and we are going to play with the width and use 1024 just like we did for the directional light. And the height is going to be the same, so it's a square, which is logical. And we get a better result. As you can see, the quality of the shadow is better. Be careful, we have our spotlight doing this shadow, and this shadow is the spotlight, is the shadow from the directional light. Don't mix them. Then what we can do for the amplitude is play with the field of view, because the camera right now, we use the spotlight, so we are getting a perspective camera, because doing the runner is exactly what you can see here. For the directional light, we had a orthographic camera, but for our spotlight, because the spotlight is doing like a flashlight, a cone like this, well, we can use a perspective camera to see what the light can see. So yeah, this is a perspective camera, and we can control the field of view of the camera. All right, it's the field of view of the camera. Let's change it, and we are going to use 30, which is 30 degrees. Camera field of view, so it's just FOV equal 30. And here is the result. We have a very, very, very small amplitude, so it's really small. If we move our sphere just slightly on the right, it's not going to work, so be careful with that. Anyway, we have a better shadow quality. And then we can change the near. So this is the near, it's way too close, and the far, it's way too far. And we're going to use, I think it's really close to the value we had for the directional light. It's going to be near equal 1. Let's just see the result. Yeah, you see it's much further. Can do even 2, but let's keep 1. And the far is going to be 6, which is going to be right here. And it's great. It's maybe even too far, but you never know. Like the shadow can go pretty far. So anyway, it's better like that. All right, cool. We set up our spotlight and the shadow. We can then hide the helper. So we're going to do visible visible equal false, and then the helper is hidden. Great. Let's add the third one that can support shadows, which is the point light, and we have few things to see about the point light. So I'm going to do right after. It's going to be point light, and I'm going to do const point light equal new 3 and use the point light class that we saw in the previous lesson. So the color is going to be white, not very interesting, but anyway we want to focus on the shadows. We can already set the cast shadow because we know we want shadows with the point light. So cast shadow true, try to remember this one. We're going to use those in the next lesson. So we are going to practice anyway. It's all about practicing what we learned. Cannot just learn something and be able to apply it on every conditions and every situations. I'm going to move it somewhere. I don't know where is it. Don't worry. We are going to see shortly. And we add it to the scene with scene add point light, and we get something like that. Yet again, it's way too bright, but anyway, we are going to add the helper right now. So it's going to be const point light camera helper equal new 3 camera helper. So as always, it's the same helper. We are just using a camera helper. And then we can pass the point light. It's going to be point light shadow, which is everything related to shadow and shadow maps, and the camera, right? It's the camera of the shadow of the light. Cool. And don't forget to add it to the scene, as always, which is why we cannot see anything right now. And we add the camera helper to the scene. We get a strange result. We are going to talk about this. Anyway, our light seems to be right here. Our scene, again, is way too bright, so we can reduce all the intensity. We are going to reduce the intensity of the ambient light and the intensity of the directional light, and I think that's enough. Yeah, we can also reduce the intensity of the spotlight. Forgot about it about this one in the examples. It's not that important anyway. So yeah, we have a point light here, which is casting a shadow here. So it's a huge shadow because the point light is really close to the sphere. The camera helper seems to be a perspective camera facing downward. All right, so we have our camera helper. This is not a light helper, it's a camera helper at the exact position of the light, and we get a perspective camera. But why do we get a perspective camera? This is strange. Well, a spotlight, we can use a perspective camera, which is logical. A directional light, we can use orthographic camera, which is logical. But how can you do a render of the surrounding? Because the point light can illuminate in every direction, so we can have shadows in every direction. And this is the harsh part. What three.js will do, which is logical too, is create a perspective camera that will look, let's say, on that direction and do a render. Then on that direction, do a render. 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 And that direction, do a render. In every 6 directions of a cube. It's like creating a cube environment map. It's going to be 6 renders of for every direction. So we get a render for every direction. We get something which will look bad probably, but something like that, something like that, something on the top like that, something on the bottom like that, something on the front like that. Okay, it doesn't look that bad, but it's a mess anyway. And we get the surrounding, right? And to do that, three.js will use a perspective camera. And that's all. But why do we see a perspective camera looking down? Well, my guess is that the last step is downward. So this is why we can see the last step. So it's doing every renders in every direction and end up looking down. So we can see the camera looking down. Okay, cool. So right now you're probably thinking that that's a lot of renders. And it is. We are doing a lot of render. If you add, I don't know, 10 point lights with shadows, you will have 10 multiplied by 6 renders before your render. So on each frame, which is a lot, which is why you have to avoid shadows as possible. But anyway, let's add it. You will see that still our GPU, our computer can handle that. So I'm going back to the point light and I'm going to do the same thing as before. Because it's a perspective camera, I can control the camera near and far. I cannot control the field of view because the field of view is made so it can render everything around. So you cannot control the field of view. And if you can, you are going to mess up with the result. So don't change the field of view, only change the point light, shadow. So you can change also the map size. So let's do the map size width, and we are going to use a pretty huge width. The same as the other, but this time we are doing 6 renders, which is a lot. Then we can play with the camera near, and we are going to, because it's very small to the sphere, we are going to use 0.1 because it's pretty close to the sphere. And we can change the far to something like 5. We're going to see the result right now. Yeah, we get something like that. The far is maybe too long, but anyway, we never know. So yeah, let's use far. It's not that important. And once we are done, we can just hide the helper by doing visible equal false. Okay, and we have a beautiful shadow right here. Yeah, looking great. So as you can see, shadows, it's a lot of work and the result is not that great. So if you have just one shadow, light creating shadows, it can look pretty good. But if you have multiple shadows and you want realistic shadows, we need other solutions. One good solution is baking shadow. And we talked about baking in the previous lesson when we talk about baking lights, like I did for the 3GS homepage WebGL experience. It's the same thing. We are just baking shadows. And actually, in the example from 3GS, the shadows were baked inside the texture. So yeah, you just bake shadow in the texture. So instead of having a real-time shadow, you get a picture of the shadow on the floor. We are just going to focus on the shadow on the floor. First, we are going to do that, but first we are going to deactivate the current shadows. To do that, we can go to the render. Instead of just commenting or removing everything we made from the start, we can do renderer shadow map enable and do false. And just like that, no shadow anymore, no drop shadow at least. Then we are going to use this bake shadow. And it's just a bake shadow I did in Blender, so it's pretty simple. It's just like I put a sphere on a plane, and I baked this shadow, the plane shadow. So how do we use it? First, we need to load this texture, and this texture is located on the folder. I can show it to you. It's in the static textures, and we have a bake shadow. We also have a simple shadow. We are going to talk about this one right after. So I'm going to put my code right here, just after creating the environment. Yeah, actually, let's do it at the start of the code. So it's going to be textures, and I'm going to load a texture. Because I want to load a texture, I have to use a texture loader. So const texture loader equal new 3 texture loader. We did that quite a lot of time. Then we can load our baked shadow. So it's this bake shadow. And to do that, I'm going to call it bake shadow. I can do bake shadow texture. Anyway, bake shadow will be fine. Equal texture loader, load, textures, baked shadow.jpg. All right. Let's see if I did a mistake here. Just log the shadow. You can do it too. No mistakes, no error. Seems fine. If you get an error, it's probably because you did something wrong with the path. I see. I get an error. Just get back to the path. Try to see if you loaded the right image. Anyway, we have our baked shadow texture. What we are going to do is move to our plane. So you can just copy baked shadow, go to the plane, and instead of using the same material as the sphere, we are going to instantiate a mesh basic material, because all we want is to show this texture instead of the current mesh standard material. We're just going to put the image of the shadow on the plane. And to put a simple image on a plane, you can on a geometry, you can use mesh basic material. And the parameter we need here is map. And we get something like this. So as you can see, it's much better. It's a soft shadow. It's not crazy, but still it's better. And it looks great. The problem is that if you move your sphere, oops, because the shadow is baked on the plane. You have to decide. We have a very static project, or you have a dynamic with object that can turn around, stuff like that. But you have shadows that doesn't look as good. But it's really depend on the project. More about that at the end of the lesson. So yeah, cool. This is one way of doing. Those are called baked shadow. You can bake shadow by using softwares like C4D, Blender, 3ds Max, stuff like that. And we are going to see another solution to fix this dynamic problem by creating a baked shadow, but a baked shadow that can move. You will see the result. First, we are going to see this shadow, and it's that. All right, it's just a diffuse, like a diffuse light, a diffuse gradient that we will use to put on a plane below our sphere. And when the sphere will move, we will also move the plane like that. All right. And if the sphere goes up, we are going to reduce the alpha of the shadow plane. And if the sphere goes down, we will increase the alpha of the shadow, and still we are going to move them together. It's not as realistic as this shadow, but still it will look pretty great. I just want to show you another technique that I use on my portfolio, actually. This is what I did for my portfolio. And it looked great, I think, I hope. Anyway, first you can get back to the previous material on the plane. So I'm going to use the material that I created sooner in the code. So just replace this mesh basic material. It was just a test with the baked shadow. So use the material. We get our previous result without any shadows because we deactivated the shadows. We are not going to use the 3GS shadow right now. Then we can load this texture, which is in the same folder. So it's simple shadow texture. As you can see, the center is white and the outer is black. The white will be the visible shadow and the black will be the invisible shadow. So we can load it. I'll just duplicate and I'm going to call it simple shadow. And it's going to be simple shadow in the name of the file too. Like this. As always, you can just log it to see if everything is right. No error. Cool, we can continue. Simple shadow. And what we are going to do right now is create a shadow below the sphere, but it's just going to be a plane right below the sphere and slightly above the floor, because if you put two planes at the same place, you will get a glitch called Z-fighting, where the GPU doesn't know which one should be seen, should be visible, and you will get glitches as a result. So we are going to create this. It's going to be somewhere, after the plane. So I'm going to do const. It's going to be the sphere shadow. So you have to do it for every object that can create a sphere. A shadow. Equal new 3 mesh. And we are going to do it right away. New, it's going to be a plane, 3 plane, but we are using buffer geometries. Buffer geometry. I don't know for the size, not that big, not that small. We will see later the results. New 3 mesh basic material. I'm going to use a color. You know what? We are just going to start with a red plane just to see this plane and you will understand what we are doing. So I'm not putting the other things. I forgot, because this is an object, you have to provide the name property, the property name. So it's color like that. I forgot to add it to the scene, so I can do scene add sphere shadow. and we get this. So this plane is going to be our shadow. All right, it's just going to be right below the sphere, and it's going to follow the sphere movement. So what we can do is position it right. First, we're going to rotate it, but we have to rotate it in the right direction. So rotate X, and because it's like a quarter of a full rotation, we have to use math pi. This is half a rotation, so we have to divide it by 2, or the way I like to do it is multiply by 0.5. Not working. It's because I did it in the wrong direction. So it's minus math pi divided by 2. And we get this. All right. So the orientation is fine. We need to get it a little below, down. And what we can do, instead of just trying to find the right value, we are going to use the plane position y. And if we do that, it's position y equal plane position y. And we get this. Oh, what's that? I told you about this. This is Z fighting. It's when two planes are at the exact same position. It's mathematically true. They are at the exact same position. The GPU doesn't know which one is above the other, and we get this really strange result. We can be really fun. Maybe we can do something with that, but it's not the subject of this lesson. So we're going to move it a little up by 0.01, which would be enough. And we get this. And now what we can do is replace this plane by the texture we just loaded. So we are going to do alpha map, because we want to use the alpha texture. So this will be visible and this won't be visible. So it's the alpha map when white is visible and black is not visible, and use the simple shadow like that. No, it's not working. Why it is not working? Because when you want to use alpha, opacity, stuff like that on a material, you have to use transparent true, right? The order is not important. You can do it after, before, it's just an object. And we get this. Nice. Okay, we are almost there, but this red shadow is not right. We have to use, let's say, black, because it's all grayscale render. And we get this result, which looks great. All right, maybe it's too much, but anyway, we are going to play with the opacity right now. What we are going to do now to test this shadow is move the sphere. So first step, we are going to animate the sphere. Follow me on this one. Update the sphere. As you can see, I'm adding this code inside the tick, because on each frame, I'm going to move my sphere. And to move my sphere, I'm going to do circles like this. And we already talked about doing circles. What you have to do is cosinus and sinus on, let's say, two axes. We are going to use the X and Z. So the X by default is there and the Z is there. All right. And we are going to animate the sphere so it does movement like that. So we are going to do this multiple times. At the end, I'm quite sure you will understand if you don't already. Position X equal, we are going to do math cos, and we are going to use the elapsed time. If you don't remember about the elapsed time, is how much second has been spent since we reloaded the page, since we loaded the page. So I can do math cos elapsed time. Now we get this. All right, it's doing like this cosinus. Cosinus is doing something like that. If you test on Google, you can do just cos X, because Google can show you this. We get this movement, so it's going up and down like that, like wave. All right, cool. We can do exactly the same on the Z, which is in the depth, but right now we are going to use sinus and use the same value inside, and you will see the result. It's doing that. All right, there is one doing this, the other one doing this, but they are offset in time, and we get this. This is a way of using cosinus and sinus. They are not moving far enough, so what we can do is simply multiply it, because it's from -1 to +1. You can do multiply by 1.5, and we get a bigger circle, all right? It's moving like that. And then we are going to do the same on the Y. What I want to do as an animation, I want the sphere to bounce. Is it possible to have the sphere bouncing? Well, we can, and because we are using cosinus and sinus will do the same, look at I'm going to use sinus because why not? Look at this. Does it look like a ball bouncing on the floor? Well, almost. This part looks good, but this part is impossible. It's like if the ball go under the floor and get up. What we want is to have this, and this again, and this again. What we want actually is that this stays positive. We want this part to be like flipped, like that. And what we can do is to use the absolute function. By using absolute, you're forcing the value to be positive. If it's minus 10, it's going to be 10. If it's minus 0.5, you're going to get 0.5. And if it's, I don't know, 5, you will keep 5 because 5 is already positive. So we can do apps like this. And this looks great, but wait a minute. Yeah, it looks like this. Boom, boom, boom. All right, it's a mathematical way of doing bouncing animation. It's not accurate, but it will look fine. So yeah, let's do this on the Y position. So it's going to be Y. We are going to use a math scene. I can use the elapsed time too. We see that it's going to be too slow, but anyway. And as you can see, it's going up and down like this. All right. What we are going to do now is use the absolute function, and we have access to the absolute function by doing math apps. All right, so this part, I'm putting it inside the math apps. And look at this. We get something like that. It bounces, which is great, and it bounces. But it's way too slow, so what I'm going to do is just multiply the elapsed time by 3. So it's inside the sinus, and we get something like that. Okay, cool. It's looking pretty good. We can do better, but anyway, I don't want to go too deep into mathematics, stuff like that. It's not the subject of this lesson. Anyway, we practice, which is great. What we are going to do now is update our shadow, because right now it's not right. And because it's just a plane, we can just change its position. So right after animating the sphere, update the shadow like that, and it's pretty simple. We can just reuse the position of the sphere. We are going to do sphere, I think it's sphere shadow, yeah, position X equal, and take back the sphere position X, and we are going to do the same on the Z, and it looks like that. It's almost there. The only problem is that when the ball is higher, you're not supposed to see such a crisp shadow. It's too visible. We want to play with the shadow opacity according to the ball elevation. So yeah, let's do that. Sphere shadow. This one is a little harder. We are going to play with the opacity. And we are going to take the distance of the sphere from the floor. What we can do is use the sphere position Y just to test. I want to test the result of this. Yeah, it seems to be working, but it's the exact opposite, meaning that when the sphere is getting high, the shadow opacity is getting high too, which is wrong. So what we need to do is 1 minus this, and we get something like that, which is great. The shadow is still a little too strong. We can multiply by 0.3. Oh yeah, be careful, I did a mistake here with the math apps. We don't need math apps right now. We could have, depending on the other factors, but you don't need the math apps, all right? And we can do 0.3. We are just multiplying it by a smaller value, and I will put it in parentheses, so it's not too big. And if you want to go even further, you can play with the scale of the plane. But we will stop there. We did already a lot. All right, cool. So this is another way of baking shadows, but still have control on the position, stuff like that. And this is the kind of things I did for my portfolio. All right. It's just shadows that I move around depending on the objects and stuff like that. Okay, cool. The problem is the question, which technique to use? Well, as you can see, you have many possible techniques. And actually, we didn't cover all the possible techniques. I just show you some techniques I use and are used by the community and stuff like that. Finding the right solution to handle shadow is up to you, okay? It depends on the project, what you can do, what you want to do. Maybe you want to try things, and you can also combine those, which is also what I did on my portfolio. I can show it to you. brunosimon.com. And when you look at this result, the shadow below the car is a dynamic shadow, but the shadows like on the trees is a baked shadow, right? It's a combination of those techniques we saw. And there is actually no light, no 3GS light anywhere. All right, so it's up to you. You have to try, you have to practice, and find the best solution.